Okay, everyone, let's get started. So today's topic is going to be the evaluation of text generation systems. So we briefly touched upon this in the last class when we were talking about the different machine translation models and comparing them to GPT-3's zero-shot and few-shot translation abilities. We mentioned the BLEU score in those tables that I showed you. So now we will explain what that means, and more generally, how can we evaluate many different types of text generation problems. So this includes translation, summarization, and then more open-ended generation tasks that are becoming more popular today. So before we start, note that you have a quiz that's due this Friday. So I set it due on Friday, so you didn't have to do anything over spring break if you didn't want to. Also note that your homework 1 requires a data set annotation exercise where you need to get someone who to annotate some data that you collect and teach them how to annotate it. So that process does take time, and you should start it fairly soon if you haven't already. Although you have till roughly the end of the month to submit this. Please use the search for teammates post in Piazza if you're having trouble finding someone. And we will try and get you the project proposal feedback by the end of this week. All right, any logistics questions? Okay, so let's get started then. So far, the only type of evaluation metric that we've actually talked about is perplexity. So remember that perplexity is a way to automatically evaluate a language model, and you compute perplexity. It's basically a function of the probability a language model assigns to some text data, right? So a low perplexity means that the model is doing a good job of modeling the data that you put in. A higher perplexity means since it's kind of the inverse of the probability, means that the model is not assigning a high probability to the sequence that you fed in. So a lot of papers that you might come across that deal with text generation have perplexity as a reported number that kind of tells you how well a model is doing compared to other models. But for many different tasks, perplexity is insufficient by itself to tell you about the quality of the generated outputs. So today we're going to look at spend most of our time talking about the BLEU score, which is useful for translation, but also is used to evaluate many other tasks, and maybe even in places where it shouldn't be used. The rouge score is kind of like a simple variant of BLEU score that is used for summarization. Both of these metrics rely on word and phrase overlap between a system's generated output and a reference translation or summary. We'll talk about improving these evaluation metrics by using pre-trained language models. And finally, we'll talk about human evaluation, so actually having humans rate the outputs of these systems. Okay, so let's focus on machine translation. You might think, how do I evaluate a system like Google Translate? So if you look at this example here, it's Chinese to English translation. Here's the Chinese. Here is the output translation. So reporters learn from the ministry, water 10 requirements before the end of this year, before the municipality, the provincial capital city, plans to build a separate city to solve the basic black and black water. Up to now, the country's 224 cities were identified to confirm the black and white water. This number, which may be a year, I suppose. At least it managed to copy these numbers, but overall, this is not really a great translation. I mean, even if you don't speak Chinese, you can probably tell that it's hard to even understand what's going on here. French to English, however, the translation quality is much better in general. We generally have more parallel data to train our machine translation models for higher resource languages like French. Also, Chinese and English are very different languages. French and English are much more similar. So if you look at this translation here, it is easy to understand and is doing a good job. So how can we kind of quantify these differences? That's the goal of today's lecture. So, and the way that we evaluate also determines how we can actually use these translation systems. So currently machine translation is not good enough for the last bullet here. If you are, say, a publisher, someone writes a book in one language and you want to distribute this book over many different countries and many different languages, you cannot use Google Translate for this purpose. It's not going to be good enough, and you actually need to hire professional human translators to do this. For communication, it is a little more useful, although still not perfect. So imagine you're talking to someone who speaks a different language than you. It would be nice if you had some sort of device that could understand what you're saying and then spit it out in a different language to facilitate this communication. So people are working on this. There are already some kind of primitive solutions, but the translation quality is still not there yet to have these kinds of handheld devices work. Another challenge with this bullet is that if you're having a conversation with someone, you probably want the speed of the conversation to proceed normally. So ideally, the translation is kind of happening in real time. Like you speak in one language, the person you're talking with is understanding you as you speak. So this is called simultaneous translation. Simultaneous translation is much more difficult than translating something after the entire text has been said. So you can imagine it's probably very painful if you have to say something like maybe 3 sentences, then all those 3 sentences get translated, and then they get read back in the language of the person you're speaking to, right? This is going to be a very slow, clunky, painful conversation. So simultaneous translation is another challenge that we have to deal with if we want to enable this kind of real-time communication. So finally, what is machine translation actually good for? It's where the reader, if someone wants to read something like some pre-written text in a different language that they don't understand. They just want to know the content. They're tolerant of a lot of errors in grammar or whatever. They just want to basically get a rough idea of the content. And as translation gets better and better, they can have greater expectations of what they can learn from these systems. So most research nowadays is focusing on this, like you have a document or you have a sentence and you want to translate it. But increasingly, we will see more focus on these other 2 bullets as the translation systems get better and better. For example, I think Mark Zuckerberg in his latest technology revealed thing said that this having some sort of device that facilitates many-to-many language communication in the metaverse is one of their goals. So probably we'll see a lot of research in this area from Meta. Okay, so let's get to the evaluation problem. One of the major challenges in any sort of text generation problem is that there's not a single right answer. So if we're doing something like sentiment analysis, right, this is a classification problem. The sentiment is either positive, negative, or neutral, right? So we can just compute the accuracy of our system against some ground truth labels and see how well it's doing. But this is not as trivial when we're looking at text generation problems. So in a generation problem, we have many possible answers. So here in this translation, these are all valid translations of this input. Israeli officials are responsible for airport security. Israel is in charge of the security at this airport. Israel is responsible for the airport security. You can see that these are all kind of paraphrases of each other. They're conveying roughly the same meaning, but in different syntactic forms or using synonyms or rephrasings or whatever. So it's very difficult to say that, okay, this first one is the ground truth translation, and anything a system spits out will be compared to this one, right? So then it'll get penalized if it spits out any of these other equally valid translations. Okay, so when we're talking about evaluation, and here we're focusing on machine translation as a case study, but in general, for any sort of text generation system, we want to know how good our system is, but we don't actually know the full set of ground truth outputs that are relevant and meaningful for a particular input. So we might only observe one reference that is human written, or maybe a couple at best, but certainly we're not going to get like, all 10 of these, or maybe there's even hundreds or thousands of these sentences that are equally valid. So there's a couple of different ways to evaluate. We'll focus on the first two. So first, you can have a human read the system output and read the source text and determine on a scale of like 1 to 5 or 1 to 100, how good is this translation? This is, of course, quite expensive. You need to have a translator who either can read the source language, or you provide them with some ground truths and they're able to make this judgment with only the target language reference. But it's expensive, it takes time, and you need to properly train your evaluators so that they're familiar with the rating system that you're using. It's much easier if you have an automatic way of evaluating your model outputs, because then you don't have to, pay people, you don't have to wait to get your evaluation results. You can just run some script and get a number. So a lot of their research focuses on automatic evaluation because it would promote, rapid development of these systems if there were such a metric. Okay, so when we're talking about any generation problem, we are usually evaluating different aspects of the output, not just like a single, how good is this translation? For machine translation, there are two important properties. So there's adequacy. So you can see here, does the output of the generated output from the system, does it convey all of the meaning of the source language sentence? So if some of the meaning, the semantics, was lost, or some new meaning was hallucinated, or the meaning was distorted in some way, the adequacy score should go down. So this is kind of distinguished from the fluency. So how grammatically correct is this generated output, and so on. So in machine translation, you might be interested in both of these aspects. So if you're setting up a human evaluation for this task, you might make some scales, right? It's common to have what's called a Likert scale, where human raters can choose from, like, on a scale of 1 to 5, where 1 is the worst and 5 is the best. How adequate was this translation, and how fluent is this translation? So you can see, though, that these categories are kind of subjective, right? What is the difference between much meaning and little meaning, right, being preserved in this output translation? It really depends on the person, right? And so this is one of the problems with all of these kinds of evaluations, is that this is a very subjective scale, and it's very hard to train your annotators so that they're using the same definition of most meaning versus little meaning. Similarly in fluency, right? What is the difference between incomprehensible and disfluent? It's really kind of a personal preference. So you might have some sort of interface developed to rate these kinds of outputs on both of these scales. So usually I try and make the class do these ratings themselves. Today we have like 10 people, so maybe this won't be so statistically significant, but let's try it anyway. So here you have the source sentence. You don't need to understand the source sentence to do this. We also have a reference translation. So this reference is something that a professional translator created as the translation. Is there not an element of hypocrisy on your part? And now you have the output of 3 systems. So for each of these 3 outputs, let's try rating the adequacy on a scale of 1 to 5. So system 1 produced, would it not as a wave of hypocrisy on your part? So remember that in our adequacy scale, 1 is the lowest adequacy, 5 is the highest. So let's see, if you raise your hand, if you would give this system 1 output a 1 out of 5 for adequacy, does it preserve the meaning of this reference sentence or not? 1 is the lowest. All right, so no one thinks this is a 1. What about a 2? Okay, one person says it's a 2. What about a 3? All right, most of you, maybe 7. How about a 4? Okay, one person, and a 5? All right, well, it's certainly not a 5, right? So most of you said 3, but there were some 2s and 4s. Let's do another one. Is there would be no hypocrisy like a wave of your hand? How many of you think this is a 1? Wow, a lot of you. Okay, how about a 2? Okay, a 3? All right, I assume no one is above that. So the class at least rated system 2 as significantly worse probably than system 1. But it's also hard, right? When you were making this decision, how did you decide to choose 2 instead of 3, right? In cases where there's an obvious difference between system 2's output and system 1's output, maybe you can make a distinction between these two, but oftentimes it's not as clear. Yeah. Yeah, that's a good question. So the question is, instead of rating all of these system outputs independently on these scales of 1 to 5 and then comparing them, what if you showed a human the output of system 1 and the output of system 2 and asked which was more adequate, right? So people do this for many types of generation tasks. The problem is, it's a good evaluation, and it should be paired with an evaluation like the one we just did, because if you get only these ranking type evaluations, then you might realize that system 2 is on the whole worse than system 1, but objectively you don't know whether like both of the systems are garbage or whether both of the systems are good, but system 2 is just slightly better than system 1. So it's a good practice to kind of pair both of these evaluations so that you get a better idea of both the kind of objective evaluation and the ranking. Did you have a question?
Yeah, like when we usually ask about rating of sentences, are we given more context? But because system 2 can be good, it was like Shakespearean, for example.
Yeah, so that's a great question. The question is, when we're doing this rating, right now we're talking about sentences in isolation, right? But usually if we're doing translation, we might not care about a single sentence, but rather like a whole paragraph or a whole document, right? And maybe we should give the whole context of the document, like the reference as input, so that the rater has a better understanding of the style or the previous content or something like that. This is a great point, but no, it's not done in machine translation evaluations. One of the main reasons is because almost all machine translation systems today are trained and evaluated at the sentence level, so they don't even consider other context from the overall document. So if you go to Google Translate and you put in a paragraph from some book and translate it to another language, you will see that you get the same exact results when you do that as if you put each sentence in that paragraph through individually and then just concatenated the outputs together. So one of the reasons is because document level translation, where you have an input paragraph or document and you want an output that's also a document, is much harder to evaluate overall than sentence level. Like the metrics that we'll discuss today don't really apply when you have much more text being compared. So this is still an ongoing research problem. People are still trying to figure out what is the best way to train these systems with more context and also evaluate them. But it's a great question. Okay, so what are some issues with this kind of human evaluation? We already talked about the subjectivity of the scale. It's also expensive and takes some time. And all of these things motivate the creation of automatic evaluation metrics. So our goal is to have some sort of separate program or script that will take the generated translations from a model and take the reference translations and possibly the source language input, and then produce a score that, like a single number that says, how good is this translation system? And we can compare that to this automatic score of other systems. So ideally here, this is a very fast evaluation to run. You can do it on a computer. It requires no human input. And you can just run it as many times as you want. So you can kind of iterate over your models by trying to improve this automatic metric. So the basic strategy for most of these evaluations is you're given the system's generated translation, you're given a human reference like we were over here with this reference sentence, and we're essentially computing some sort of similarity score between the reference and the output. So note that this has the same problem that we discussed before. If you only have one reference, you only have one instance of several hundred or thousand plausible translations for that sentence. And so this score might be misleading if, for example, your machine translation system produced a good translation, but the reference was inadequate to cover that translation. Okay, so let's start with a very basic evaluation. And the metric that we'll discuss, BLEU, is just a function of essentially the precision of words. So let's say that our reference sentence is Israeli officials are responsible for airport security. And our system generated the translation, Israeli officials' responsibility of airport safety. So if we want to try to compare the similarity of these, the system output to the reference, one thing we can do is just kind of match the words that are present in both the system output and the reference. So we can compute the precision, which means how many words in the system output were also present in the reference, right? So here we have Israeli officials. Responsibility, though, is not in the reference. Of is not in the reference. Airport is, and safety is not. So 3 of the 6 words in our generated system output also are present in the reference. Therefore, our precision is 50%. Similarly, we could compute the recall. So the recall will tell us how many words in the reference occur in the generated translation. So basically, the denominator is just changed here. So if you were computing recall, you would be interested in any kind of information that is missed by the translation that should be in the translation but isn't, right? So you want every single word in the reference, if you're interested in the recall, to be present in the system output. Okay, so what are some problems with precision and recall at the word level? Can we use these to evaluate a machine translation system? What might be some issues? Yeah.
In this case, it will try to hold the reference as the ground truth. If it differs from it even a little bit, it will say that it's not good.
Yeah, so that's one major issue, is that we have a single reference and it might not be representative of all the possible valid translations. So our system could be penalized. You know, like responsibility could actually be a word in a plausible translation of this sentence, but we get no points at all for producing this. Are there any other issues? Yeah, exactly. So what if the system produced the negation of the sentence, which has the complete opposite meaning and is not at all a good translation? In fact, it's probably one of the worst translations that you could produce. That would actually get very high scores, right? Because it differs in only one word. And so like its recall would be 100%, right? So that's definitely not good. Yeah, so like the word level of computing these stats at the word level leaves you open to all sorts of errors like these. Okay, so one of the other issues is that there's no penalty for any sort of reordering. So if I had system B, which output airport security, Israeli officials are responsible, this gets 100% precision and recall despite the sentence not being grammatical, right? Because all the words are present, they're just not in the right order. So still though, precision and recall of words is very easy to compute, as you can imagine. All you need is a way to tokenize your outputs and your reference. So that means, in this case, you would want to split the string into words, and then you would just compute this metric. So is there a way to make this kind of better and reduce some of the problems that we discussed? So that brings us to the BLEU score, or the bilingual evaluation under study, which basically extends the precision of words to the phrase level. So now we're going to compute not only the overlap of words, but also the overlap of bigrams, trigrams, and fourgrams. And then we're going to take the geometric mean of all of these precisions and use that as our final score. So the precision mean computation is here. You see that we're computing the precision for n-grams of size 1 to 4. Then we're doing this mean. There's also this brevity penalty. So the BLEU score, as we'll discuss later, does not take into account the recall computation. So as we showed here, if we compute the recall, we can also just compute the F score via harmonic mean, and then we can use that as our final evaluation. But the BLEU score, for reasons we'll discuss later, does not include the recall. As such, it includes something that's kind of analogous to the recall, which is this brevity penalty. So if the reference, if the generated translation is too short, it gets penalized through this, basically just the output length divided by the reference length becomes the penalty. So you might want to do this in the case that, what if your what if your system produces like Israeli officials are responsible and nothing else, right? It might get a high precision score on most of those n-gram statistics, but it's dropping some critical information. So possibly the ratio of the length of this translation to the reference is a valuable thing to include. Finally, we compute this BLEU score over the entire corpus, and although it is also kind of informative to compute at the sentence level, but typically it's much more useful when averaged over the entire corpus, because as you can see, it's kind of noisy, right? For a single sentence, maybe you just got a paraphrase or something like that, and the BLEU score turns out to be 0. But on a large held out corpus, the BLEU score starts to become more reasonable. So people typically report it over an entire large test set. Okay, so we discussed why what this brevity penalty is, but why does BLEU score not use recall? So one thing that you may want to do if you are evaluating a translation system or any sort of generation system is if you have multiple reference translations. So let's say we had 4 different reference translations instead of just 1. So we had our original one, Israeli officials are responsible for airport security, but then we also have Israel is in charge of the security at this airport and these 2 other ones. We would like our metric to be able to use all of these references in the process of coming up with this score. So how do we do that? If we're talking about precision, it's very easy, right? Because I can take, let's say I'm looking at the bigrams, I can look at Israeli officials, and I can see if in any of the references there was this bigram Israeli officials. If there was, I get some points for that. If not, I get no points. Similarly, I can look for this phrase responsibility of, which note that it's not in the first reference, but it actually does occur in the 3rd reference. So now this bigram could be totally reasonable as part of a translation, and because I was able to use this reference as well as this one, now I actually get some points for producing this bigram. So precision is very useful when you have multiple references, because you can just compute the precision over the entire, all of the bigrams and trigrams and fourgrams in all of the references. The recall computation, though, is a little trickier. So why might we not want to compute recall in this case if we have multiple references? Yeah, so if we're computing precision, right, we're just saying that any bigram that matches one in the generated system in any of these references is considered a match. But think about what the recall is doing. The denominator is now the total length of all the bigrams in the references. We have multiple references, right? So we would be asking the system to get match Israeli officials, match Israel match Israeli side. No single translation will include all of these possible variants of this phrase, right? Similarly, responsibility of, and if we were computing recall, we would be asking the system output to include responsibility of, responsible for, in charge of, and all these paraphrases, right? So the recall score is not meaningful when we have multiple references. The precision, however, is. So that's why BLEU is a precision-based metric, but also includes this penalty for short translations, which is kind of a mirror of what the recall would be giving us. All right, any questions? Yeah, this is a great point. So in this computation that I've described, a stop word like the or and is treated exactly the same as an important content word like Israeli or airport, right? So if a model drops the, it's treated as the same penalty as if it drops Israeli, which obviously should not be the case in a metric, right? We want the metric to, if we're interested in adequacy, obviously the latter is much more important than the former, Israeli versus some function word. So this is a problem with BLEU because you're just using word overlap and not ranking the words. We'll see that the more advanced metrics that are built on pre-trained language models don't have this problem. So it's kind of a trade-off between how complex you want your metric to be. This is obviously extremely straightforward, and how expressive it actually is. So BLEU was very useful when machine translation systems were bad, because there were potentially large gaps that you could get in the BLEU score that would tell you that clearly system A is better than system B because its precision of words and bigrams is higher. But nowadays, our machine translation systems are much better than they were even 10 years ago. And BLEU has almost ceased to be a meaningful measure of the difference in quality, probably for reasons that you described. Maybe now, it's much more important to focus on certain words or phrases that are much more important to the meaning than others. And so that's why the learn metrics now are taking over. But we'll get to those in a bit. Okay, so let's go through some of the computations just to make sure everyone's on the same page. So let's say that we have system A. It produces Israeli officials' responsibility of airport safety. And we have just one reference translation. Israeli officials are responsible for airport security. In the BLEU score, we're going to compute the precision at different n-grams. So our 1 gram precision is just the word level precision. We already computed this before. What about our bigram precision? So here we have 5 bigrams in system A's output. So we have Israeli officials responsibility of airport and airport safety. Of those, only one of the bigrams matches, right? Israeli officials is in the reference and in the system output. So we get a 1 out of 5 precision score here. And if we go to trigrams, there are 4 trigrams, and none of them in system A occurs in the reference. So our system gets a 0 precision for this. And remember that we're computing the mean of all of these scores. So overall, our BLEU for the sentence is 0. So the system got no points at all for producing this translation. Now, you can argue that it shouldn't be a 0, right? It's not a good translation, but you can get some sense of the content here, even though it's not grammatical. System B, we have airport security, Israeli officials are responsible. So you could argue that this is worse than the translation in system A, because it's not in order, the content. It's kind of hard to interpret what's happening. However, system B is perfect on precision, and it also has at least one matching n-gram for all unigram, bigram, trigram, and fourgram. This fourgram, Israeli officials are responsible, matches with the reference. So the BLEU for this sentence B's output is 52%. So this, again, is one example of why you might not want to interpret the BLEU scores at the sentence level, right? Because it's kind of noisy like this, and just because system A's output was 0 on the BLEU score doesn't mean that it was completely bad. However, when aggregated on the corpus level, the BLEU score, the average, turns out to be meaningful. Okay, so we already talked about why BLEU doesn't account for recall. So let's just highlight some of the drawbacks of this. First, as to your point, all words and n-grams are treated as equally relevant, which is bad. This operates on a local level, right? So when we're considering an n-gram, we don't consider any of the other context in the sentence, which might help interpret what that bigram was. The scores are meaningless, so the absolute value of the score is not really informative. And to kind of second that, human translators also score pretty low on BLEU. So, you know, like a BLEU of 100, it means basically you have to almost exactly match the reference output. But human translators themselves have a lot of variance in what they produce. So the upper bound on BLEU score is not 100, and it varies from language pair to language pair. It's kind of hard to know what the maximum achievable BLEU is. That said, with all that said, like this is a bad, it has many negatives about it, it does seem to correlate the BLEU score with human judgments of adequacy and fluency. So on the y-axis here, you have a variant of BLEU called the NIST score. It's working very similarly. And on the x-axis, you have these human judgments on adequacy in the red and fluency in the green. And you can see that when the automatic score, the BLEU score, is low, the human judgments are also quite low. And when they're high, the human judgments are also high, and the correlation is pretty clear. So studies like this, where you have a metric and you correlate the output of that metric to human judgments, these studies kind of validate that this evaluation metric, despite all its flaws, is still a useful automatic way to evaluate your translation system. So when new metrics are proposed, they basically have to show that they have a higher correlation to human judgments than existing metrics. So if I wanted to make something better than BLEU, I would have to show that it has a higher correlation to these human judgments. So that means that the quality of the human judgments is critical to automatic evaluation, because when you make a new metric, you're always trying to get it the closest to how human translators would, or human raters would, score these system outputs. Okay, and we're not going to talk about this in detail, but rouge is basically a recall-oriented counterpart to BLEU. It's also focused on overlap of words and n-grams, and it's used in summarization. So it's not used in translation, it's used in summarization. The basic idea is what percentage of the words or the n-grams in the reference occurred in the generated output. So note that in BLEU score, we don't use the recall at all. In the rouge score, we're primarily using the recall. So why might this be useful when we're evaluating a task like text summarization? Let's say we have one reference summary and we have a system generated output. Yeah, exactly. So if we have a reference summary, intuitively this metric will say that, all of the words and n-grams that occur in this reference summary are very important. They're probably the most important parts of the document. And we want our generated system our system output to have all of those words. Now, the generated system output could also have other things, right? Maybe it picked up on some things that are not as important, but maybe it shouldn't be penalized too much for doing so as long as it includes all of the important content. So you can also see an obvious way to kind of game this metric, right? Because the point of summarization is that the summary should also be as short as possible, right? It should include only the important information and not anything more than that. But since rouge is a recall focused, you could potentially have a system that produces very long summaries, maybe like the entire document, right? And then you would kind of max out this metric, but it wouldn't be a useful summary. So there are challenges in summarization that the rouge score by itself doesn't really cover. So there are variants of rouge that kind of account for these things, but the rouge, again, just like the BLEU, is a very, very simple metric that you can easily compute without any sort of, or GPU requirement or anything like that. All right, so any questions about rouge or BLEU? So the question is, can we say that BLEU does not penalize things like grammatical correctness? I would say it's hard to answer that question because it does to some extent. Like if you're talking about a 4-gram match, a 4-gram has 4 words in it, and you're only going to get a match to the reference if those 4 words are in some sort of meaningful grammatical construction, right? So that's the whole point why they extended from 1 to 4, is that when you look at a phrase, now you're getting some more local syntactic matches into your score. That said, it's still very local, right? So you can have like these local, as we saw in this example, like this is getting points for this match, even though this 4-gram is not in a grammatically correct location considering the entire context of the sentence. So I would say, like, maybe on a very local level, it includes some aspects of grammaticality, but not on a global level. And you can especially imagine if your translations are long, the BLEU score is not going to give you like some sort of syntactic rating or anything like that. Other questions? Okay, so we have nothing from YouTube as well, so let's continue. One natural question, because we've talked at this point in the semester basically exclusively about these large pre-trained language models and how they have set state-of-the-art numbers on almost every NLP task. One natural question is, can we use these things to have a better metric than the BLEU score, right? Because the BLEU score is very limited in all the ways we talked about. Maybe some of these pre-trained models don't have the same limitations. So we can ask the question, can we actually learn the evaluation metric instead of just using this kind of overlap as the evaluation score? So one of the readings for today was the BLEURT paper, which very cleverly combines BLEU and BLEURT together to form BLEURT. Basically, they take a pre-trained BLEURT model. They have a bunch of these synthetic pre-training tasks, which are really not super critical to understand. But the main thing that they do is they take all of the human judgments. So we talked about these, these human judgments that we ask people from 1 to 5, how adequate is this translation compared to the reference? How fluent is this? So over the years, many data sets of these human ratings of translations have been collected. So they now have on the order of like 100,000 or so sentence pairs with these human evaluations. So given this, you can actually train a model to, given a translation, predict the human score, like predict from 1 to 5, what would a human have said about this translation given this reference. And now you can use this as a training objective. So you want your model to predict the human judgment. And then at test time, when you get a new translation and you have a reference associated with it, you can pass those through your model, and your model will predict, you know, what it thinks a human would say about this translation. And you can use that as your evaluation score. So this is leveraging all of the important stuff we learned from pre-trained language models, right? The pre-trained language model definitely has a better global understanding of the sentence, right? It's not limited to just these local n-gram matching. It takes into account probably much more semantic meaning. It, as you pointed out, it probably gives much higher weight to important words rather than stop words. So there are all of these advantages. And it's being trained to mimic the human ratings. So this is the new generation of evaluation metrics. Let me go back to where I was. So you can see that if you just ignore all of these sub-bullets, which are things that were proposed in the BLEURT paper that maybe are not too critical to its performance, you take a pre-trained BERT model, like we've seen with pre-trained with masked language modeling, and you fine-tune that model on small supervised data sets of human quality judgments, and you have your final model. So this has higher correlation with human judgments than BLEU, but there are limitations. So what does some of you think are some limitations of this kind of approach, where you use a pre-trained language model and fine-tune it to predict human judgments? Okay, well, one question is, will this work on every language? Why might this not work on every language? Exactly, right? So there are two reasons. One is you need a fairly large data set of these human judgments of translations. Those are certainly available for, you know, translation into English or other higher resource languages, but they probably are not available at scale for many low resource languages. So this approach is not really feasible in those settings. Another kind of related reason is that you also need a pre-trained language model in that target language, right? And while this is easy to get for English and French and German and so on, it is harder to get for other languages, like a similarly scaled up pre-trained language model that's been trained on lots of data and is sufficiently large. This takes a lot of compute resources, time, and money. These models have not been made available for every single language. So while the BLEU score requires a tokenizer and then just some overlap, this requires, it has much more stringent requirements. You need a large labeled human judgment data set, and you need a large pre-trained language model. So that said, there are some ways to get around this that we'll talk about at the end of class if we have time, but yeah. Yeah, that's another good question. So the point is, wouldn't the problems with these human judgments, like how subjective they are and how calibrated the raters were on the scale, wouldn't those really affect this because it's trained directly on those judgments? Yes, the answer is yes. And there have been many recent studies that show that the human judgments that these models are trained on are extremely noisy. So BLEURT is actually trained on a bunch of data where annotators were asked to label how good is this translation from 0 to 100. So they didn't even separate out like adequacy or fluency, and 0 to 100 is just a ridiculous scale, right? They basically had a slider and they could you know, slide it around, but it's very hard to decide, you know, is this like a 78 or a 72, right? It probably is an impossible choice, really. So there's a lot of variation. People have done some analysis showing for the same system output, there was huge variance on different annotators' decisions. So I think one next step for this kind of work is obtaining a much higher quality set of human judgments on different dimensions. So don't just collapse translation quality into one 0 to 100 scale, but another problem with these, related to your point, is that most of the human judgments are not collected from experts. So basically, the community recognized the need for having these human judgments at some scale. And every year there's usually a competition for machine translation systems. There's a workshop called the Workshop for Machine Translation, or WMT. They generally release a data set and they say, all right, go build your systems, and whoever gets the highest score wins this year's competition. One of the issues is the evaluation is done not only by automatic metrics, but also by humans. So they ask humans to rate all these system outputs and figure out which one is best. But they run into the problem of, how do we get these human annotations? They don't have that much money or resources. So they end up asking, if you submit a system, you're also required to rate other system outputs. So now you have like computer science students or industry researchers who, might not be the best population to do these ratings. They're performing these ratings on like a scale of 0 to 100 instead of professional translators or experts who know both languages or things like that. So yeah, it's a huge issue. They're trying to work to solve it, but it will take some time. Okay. So now we can talk about COMET, which is another kind of variant of the BLEU score, of BLEURT, also a learned metric, but it's very straightforward. So unlike BLEURT, so BLEURT basically just takes in the reference sentence and the generated output and gives you a score. COMET also takes in the source sentence into account. So if you see here, you have an input sequence that you create, which is the hypothesis. So this is the model's generated translation. You have the source sentence, and you have the reference. So we haven't yet talked about multilingual language models, but if you imagine this kind of input, your hypothesis and your reference are going to be in a different language than your source. So I can't just use BERT for this task, right? Because BERT is trained primarily on English text. I need whatever this encoder is to be multilingual. So it should be able to handle multiple different languages, potentially in the same input. So in COMET, they use a multilingual language model called XLM to perform this encoder step. Now, after I pass this input sequence through my encoder, I have all these token level representations, right, corresponding to each position of this input sequence. I'm going to apply what's called a pooling layer, which is essentially a composition function to kind of aggregate the representations across the different tokens. They concatenate those outputs and pass them through a feed-forward layer. And this feed-forward layer will go from this giant concatenated vector to a dimension of 1. So it'll output a scalar score. So this could be like between 0 and 100. And then you train it with the square loss that we saw. So if given this input sequence, the model predicted the number 78, and the reference, the human judgment for this particular translation was like 64, right? I can compute an error based on that, and I can backpropagate it into my model. So next time we see this, the predicted score will be closer to 64. So it's very simple, basically just requires that you have this pre-trained encoder and you add some small number of parameters on top and fine-tune the entire model to predict these human judgments. So there was a paper here that I think one of the readings for today that showed that in almost all cases, if you can get this COMET model, like you have the human judgments and you can fine-tune it, it's almost always superior to the BLEU score in terms of correlation to human judgments. And so it's highly recommended if you're doing translation to not only report your BLEU score, but also your COMET score and A couple of months ago, Google released a new upgraded version of BLEURT, which I think could be even better than the COMET model. So if you're interested in the state of the art, you can check that out. Okay, so any final questions on these kind of learned metrics? All right. So in the last part of this lecture, I want to kind of switch tasks. So we've been talking about translation and a little bit about summarization. These are on the more constrained end of text generation. So we discussed how translation and summarization, you can have multiple valid outputs, but they're still roughly all paraphrases of each other. They have the same semantics, right? You want to preserve the meaning of the source sentence. So your output space is kind of constrained. But there's a different class of problems where the output space is not anywhere near as constrained. You might have, for instance, story generation, where you're given a prompt, like you, a video game character, just died, you have no spare lives left, and then you ask a model to generate a story that is inspired by this prompt. So why do you think that the BLEU score might not be a suitable way to evaluate this kind of task? Exactly. So like this, if this is my only reference, right, it's incredibly specific. It, first of all, chose a specific video game character, wrote some stuff about that character, but I could have certainly a completely different story that chooses a different character, right, and is still inspired by the prompt and still enjoyable, still relevant, but has a very low string overlap to this reference. That said, you know, there are data sets for this kind of thing. So this data set is formed by the writing prompts subreddit, where people post these like short prompts and then other people write stories in response to them, and then they get rated by like upvotes and so on. So because this data exists, NLP researchers are like, oh, let's work on this task where we try and generate these stories. And it's very easy to come up with models for this kind of task, right? Because for this, like, what are some different models that I could use to solve this task? If I wanted to, given a prompt, generate a story, how might I go about building a model for that? Sure, that's one thing. I could take GPT-2, I could put the prompt in, maybe add a separator token, and then put the story in, and then use like prefix language modeling or just normal language modeling to fine-tune it to generate these stories. Are there other approaches based on all the stuff we've seen so far? So like any language model would work, right? I could use a sequence-to-sequence model like the T5, right? I could put this prompt into the encoder and then have the decoder fine-tuned to produce the story, right? Any sort of language model that we've seen is totally acceptable for this kind of task. So it's an interesting point where the models we have can be easily trained to solve all of these kinds of problems, but we don't have a way to evaluate how good they are. So here I'm going to just show some of the challenges with human evaluation, because we certainly don't have any automatic way of evaluating these. We can't use BLEU, we can't use BLEURT, we can't use COMET. All of these things are highly reliant on the output being very similar to the reference. But in an open-ended generation task, the output is almost never going to be similar to the reference, even if it's valid. So setting aside automatic evaluation, we still have human evaluations that we can try, right? We can show our model-generated stories to human raters and ask them to rate the text on various properties. So this is what's commonly done with all of these open-ended tasks, is that people will go to a platform called Amazon Mechanical Turk. How many of you have heard of this? So basically it's a place that you can, it's a platform run by Amazon that you can post these small tasks, like given this paragraph, rate it from 1 to 5 on how grammatical it is. And so I have an example here. Like you can say, how grammatically correct is the text of the story? And you can post this task to a huge crowd workforce. So these are people who have these Mechanical Turk accounts and they do these small tasks for payment. So you can pay, like 15 cents per judgment or something. And your tasks get done very quickly because there are tens or hundreds of thousands of workers who could potentially do all your tasks. So usually when we launch one of these jobs, it completes in like a day if you want hundreds or thousands of judgments. You have to pay, but it's definitely faster than, say, recruiting a bunch of people and then teaching them how to use these guidelines, and then that could take weeks. But this thing is very fast. So most people in open-ended generation use Amazon Mechanical Turk to evaluate their model outputs. So given a prompt, so basically, like, one question you might have is, how reliable is this kind of crowdsourced evaluation of open-ended text generation? Given that this is the go-to evaluation for these kinds of tasks, are they actually meaningful, or do they also suffer from problems? So one way that you can measure this is by seeing whether the raters of these stories will rate human-written stories higher than model-generated stories. So as you said, we can train a simple language model like GPT-2 to generate these stories conditioned on the prompt. And just qualitatively, you can read the generated text and you can tell that this is not a good story, right? So here, given this video game character prompt, the generated story from GPT-2 is the US space station exploded with automatic fire in preparation for tonight's nuclear strike on Earth. I'm not sure why that would happen. This is video. Here's a figure wearing a manila envelope, which doesn't make sense. Falling off the back of the space station somehow while detonating a device. An audio file is made. I mean, it doesn't really make sense. It's not coherent. It's probably not very relevant to this prompt. So compared to the reference story, at least. And it also suffers from, like, what does this mean, a figure wearing a manila envelope, and so on. So we can send both the human-written story and the model-generated story to this platform, Amazon Mechanical Turk, and we'll ask the workers to rate how grammatically correct is the story, how coherent is the story. So this is coherence is measuring if you have multiple sentences, how well do they fit together? Are they telling some logical narrative, or do they not make sense? Likability, of course, enormously subjective, but basically this is what you kind of want to evaluate in the end, right? Like, how enjoyable is this output to read? The problem is it's very subjective. There's extremely high variance. Some people might find the story about Link fascinating if they're a fan of the franchise. Others may not find it very compelling. Finally, relevance. How relevant is the story to the prompt? So you can ask these raters to rate the machine-generated stories and the human stories. And one interesting finding that my postdoc found in her experiments was that the Mechanical Turk workers cannot distinguish between the machine-generated and human-written stories on these different metrics. So if you look at grammar, we had 3 different days where we rated the reference stories, and 1 day where we rated the machine-generated stories, and you can see that the mean score, this is from 1 to 5, it's hard to tell which one is more grammatical. Coherence, it's a little lower, but probably not significant than the human-written stories. Relevance, again, it's a little lower, but hard to tell. And likability, like, it's, roughly the same. So overall, in this rating scheme from 1 to 5, these Amazon Mechanical Turk workers were not able to distinguish the GPT-2 stories from human-written stories. So from this table, we could conclude that GPT-2 is writing human-quality stories. But that would be incredibly wrong, because we ourselves could read the stories and we clearly saw that the GPT-2 stories were worse. So if you inspect what is actually happening, it turns out that these workers are spending almost no time reading the written text, and the median time for one worker who did a lot of these ratings was 13 seconds per story. So in 13 seconds, you have to read a story that's much longer than this. This is just a snippet, and rate it on all 4 of these properties. Basically, you can take 13 seconds to just click the slider values for each of these without reading anything. So one of the biggest issues with these kinds of crowdsourced settings is that the workers have different incentives than you do. So you're interested in getting accurate evaluation of your model outputs. The workers are interested in getting as much money as they can in as little time as possible. And they don't really care about your task. So you need to very carefully design your task to more to give them no chance to cheat in any way possible. And that's very difficult to do. So we wanted to see if human evaluation could be done better in these cases if you hired actual expert raters. So we went out and got 3 English teachers and had them rate the same set of stories. And we found that they were easily able to tell that the human-written stories were superior to the machine-generated stories. So while grammaticality was about equal, which is kind of expected because the pre-trained language models don't make that many obvious grammatical errors anymore, and also humans on Reddit, make a lot of grammatical errors. But in coherence, relevance, and likability, the human-written stories were significantly higher than machine-generated stories. So the moral of this story is human evaluation is good, but you have to kind of pay, you have to let it take time, and you have to be very careful about who is doing the ratings, because otherwise your evaluations are going to be meaningless. And in that case, without this kind of expert human evaluation, we have no way of assessing a model's ability to solve any sort of open-ended text generation task. So even the English teachers, it turns out, struggle with this task, because you might not think about it, but reading and rating machine-generated text is not something an English teacher has ever done, right? So there are weird artifacts that are present in machine-generated text that are not what you would see in like a student's writing if they're making mistakes. So they found that coherence, so the relationship of different sentences in the story, was very difficult to rate for the machine-generated stories, but it was very easy for human-written stories because they were largely very coherent. GPT-2 makes some weird errors, as we saw when we were discussing the different decoding algorithms, right? They tend to repeat themselves over and over or hallucinate new entities. These are not phenomena that human writers, even like new writers, will do. They won't just repeat the same phrase over and over again. So it's very hard to decide how to score this, even if you have been an English teacher for like 20 years and have graded numerous papers. It's still non-trivial. We found that the average time that it takes to rate even one short story for machine-generated text is much higher than it's like 87 seconds per story compared to human-written stories. So that also indicates that there's some significant mental load when you're reading a machine-generated story that's not present when you're reading a human story. And also, like, this is about the time you would expect a Mechanical Turk worker to take if they were accurately or closely reading, instead of 13 seconds, which is just completely ridiculous. Okay, so what are some takeaways? First, evaluating these tasks is extremely difficult, even if you have expert raters. Just because you can make models for some of these things doesn't mean you will know if they work or not. And the field is kind of at a place where the modeling advances are there and they can solve you can train them to solve these different tasks, but the evaluation advances are not yet there. So we're now seeing a lot more work on evaluation metrics of increasingly more open-ended tasks to kind of make progress on research in this direction, and actually solve generation problems that are not translation or summarization. Okay, so there are other instances of open-ended text generation tasks than story generation. There are more useful ones. So one example is question answering, where the answers are paragraphs, right? This is a very important future direction for NLP research. Instead of like the squad style, here's a span that answers your question. What if you actually had a model generate an answer that kind of explains some concept with examples and things like that? We have models that are capable of producing outputs like this, but we don't actually know how to evaluate them yet. So to get to that point where these models are useful for actual real-world applications, we need to focus on evaluation. All right, so any questions?
I was going to ask about that question answering thing, because we already have standardized tests like those like that. And when you finish with the exam, they give you like a rough condition score, and they tell you like after 48 hours they give you the actual score. So if there's like progress in that area, then that is like eliminate the human worker, for example.
Yeah, are you talking about like test essay grading? Yeah, so like the ETS, the Education Testing Service, I think they're the ones that administer the GRE. They actually have a fairly large NLP research division that is dedicated to automatic essay grading. As you can imagine, this would be extremely useful for them to cut out the human raters. And they even like publish papers at NLP conferences about new metrics for measuring things like coherence or so on. I think I'm not sure what they do, but I have to imagine that they are still using mostly human evaluations for those things, which is why it takes time. It'll be very hard to move away from that completely, just because a lot of the things that the human raters are looking for are maybe quite subtle and not easy to pick up by any of these automatic methods. But they could be useful in some sort of first filtering step or something like that before a human looks at them. Or maybe like they could be useful to first noisily identify some issues that a human can then look at. I don't know, but they've had this kind of research going for many years now. You can check it out if you are interested. I'm not sure what progress has been made. Other questions? Okay, so next week we do not have class because it's spring break, so we will continue the following week with multilingual language models, and the midterm will be either the last week of March or the first week of April, so we'll have a review session before then, and I'll announce the date. All right, so have a good spring break.